Well, we're in Chapter 4, Probability Distributions, Part 3, and we're describing the Poisson distribution. Let's look at a Poisson process first. Consider a type of event that is reoccurring. So, for instance, telephone calls that you receive in a given hour. Telephone calls recur. And maybe we want to know the probability that we get 3 phone calls, or 2, or 1, or 0. Or it could be, let's say we have a long piece of wire and we want to count the number of defects on this piece of wire. And so the recurring event would be a defect as we progress down this wire. If we let x of t, now note that t, it's a function of how long we observe telephone calls or how long the piece of wire is. So the number of such events that occur in a given interval from 0 to t. And we let P of n of t equal the probability of n occurrences in the interval 0 to t. Then this random variable can be modeled as a Poisson. So it's the probability that we see n occurrences of the event in interval t, from 0 to t. Now sometimes we'll still just call it x, but we have to know the time interval. So x is the random variable, so the x equal n, that can be modeled with a Poisson random variable. So if we look at the Poisson distribution, a random variable x has a Poisson distribution with parameter lambda. So lambda governs how frequent we see the events or how infrequent we see the events. And it's a population parameter. And usually we have to estimate it. But this is the density of discrete type, or the probability mass function. So f of x, that can be thought of, so f of x, of course you have to say given lambda because you have to know what it is. That's the same as the probability as our random variable equals some value, of course, given whatever the lambda parameter is. And this is it. That's the density. So if we want to find the probability that we see 0 defects, you plug in 0 here, and 0 factorial, which is 1. And then this tells you the probability associated with it. So let's do some examples. So the number of calls, let's call it x, that arrives at a switchboard during 1 hour is Poisson distributed with mean 10 or lambda 10. And lambda is the mean of this Poisson process. So find the probability of occurring event in an hour of each of the following events. Exactly 7 calls arrived. So we want to find the probability that x equals 7. So we plug in 7, that's this value, into the density function, and this is it. So there's a 9% probability that we get exactly 7 calls. Now notice this value here, the 10 and the 10, that's lambda. So you have to know what its mean process is, right? So that's lambda and lambda. Now what's the probability at most 7 calls arrive? So at most means that it could be 0, could be 1, could be 2. Now, the probability of x equals 0, or x equal 1, or all the way to x equal 7. That's the probability we're trying to find. That's what this is. Now, I got a question for you. Can you receive 1 call and, say, 5 calls in 1 hour at the same time? Remember, you're looking at the total number of calls. You can't. So these are mutually exclusive events. So we add the individual probabilities, and that's what this is. We let x go from 0 to 7, and we do this calculation as 22%. Now, the probability between 3 and 7 calls, inclusive, so 3 and 7 are included in that. And since the values are mutually exclusive, we can add them, and there's a 21% chance that we see between 3 and 7 calls. And it makes sense that this is less than that value, right? Because this is including, 0. This one is including 0, 1, and 2, where this one is not. Now, to find the probability that we're exclusively between 5 and 15, since x is discrete, that really means, greater than or equal to 6 and less than or equal to 14. And again, we sum the values of the density, and we get 84.9. To find this in R, or using R, the density, that's what this is, of a Poisson, and we want to find the probability that it's 7. So we're doing these examples again. Lambda's 10, and that's it. That's the probability. Now, at most 7 calls, so that's the CDF of 7. So that's the P, the probability, a cumulative probability of a Poisson at value 7, right? Probability that x is less than or equal to 7. That's what this is telling us. It's Poisson, so we need the value of the lambda parameter. It's 22%. Now, here we want to find the probability we're inclusively between 3 and 7. And this colon, remember, that expands to a vector of 3, 4, 5, 6, 7. And we want the density of a Poisson for these values. Lambda's 10. So it pumps it out. So this is the probability for 3, 4, 5, 6, and 7. But that's not what we want. We have to add them. And so that's why we sum these probabilities, and we get 21%. Now, we could have used the difference of CDFs. So the probability that we're between 3 and 7, so that's the CDF of 7, and then we want to subtract off 2 and below. We don't want to get rid of the 3. And so that's what this is. So this is the CDF of 7, and then we're subtracting the CDF of 2, and we get the same number. Now, to find this probability, so that's really 6 to 14, so it's the CDF of 14 minus the CDF at 5, and it's 89%. Of course, we could have, so the density of a Poisson from 6 to 14, right? That's what we were looking here, lambda 10. So it creates that vector of density values or probabilities. We want to sum it, and of course, we get the same thing. Now, let's jump to continuous probability distribution as opposed to a discrete distribution, which we were looking at in the previous section. Now, a continuous random variable is a value that takes on infinite number of possibilities, within a given range. Sometimes the range is all real numbers. Sometimes it's an interval between A and B, for instance. But if it can be theoretically any of those values, then it's a continuous random variable. So unlike a discrete, which has distinct values, i.e. countable outcomes, continuous assumes values within an interval. So it's an infinite number of values. So examples would be height, weight, temperature. Those would be continuous random variables. The density, the PDF, the probability density function, is denoted by f of x. And so f of x tells us the likelihood of something happening. Technically, in the continuous case, the probability of a point is 0. And so technically, this is not probability, but it's like probability. So it just describes the likelihood of the different values of occurring. To find probability, notice it's not assigned to individual points, but it's rather to intervals. And in calculus, we use a technique called integration to find these probabilities. So probability is the area under a curve. So this density, the PDF of a continuous random variable, creates a curve, and then the area under that curve is probability. And we'll see some that in some examples. So to find we have a continuous density and we have a random variable, and the probability that X falls within an interval is we calculate the area under the density curve from A to B. So using calculus, which we're not going to assume knowledge in this class, is the probability that X is between A and B is done using this. Oh, no comma there. So it's the area under the curve from A to B. And let's look at an example. So let's say X represents the time in minutes someone spends waiting at a bus stop, and it's modeled with a uniform distribution between 0 and 10 minutes. And so the PDF is this. So it's 0.1. And let's look at the height of that. So the values from 0 to 10, and this height is 0.1. Now I want to, and so next we want to find the probability that a person waits between 3 and 6 minutes. So we want to find the probability that the wait time has been between 3 and 6. And so it's technically the area of the rectangle. It's the area under the curve of the density. So 6 minus 3 is the base, and the height is this, and so whatever that number is. 0.3. Okay. So this is how we plot this density function. I shaded the area and read the text. But I want to note some things. So let's look at Kolmogorov's 3 axioms of probability. So this is only defined from 0 to 10, and it's 0 everywhere else. So these dots represent likelihoods or probabilities. Technically, in any continuous distribution, you can only find probability of intervals. But if you let this interval get really, really, really small, then it limits to that value there. So it's like the probability, the height is the probability of an infinitesimal interval around that point below it. But it's technically 0, but it limits to that value. So probabilities are always greater than 0. If you were to look at the area of this sample space, so the base is 10, the height is 1 over 10, so the area of this rectangle is 1. And if we were to look at mutually exclusive events, so let's say we want to find the probability that we're between 3 and 6 or 1 and 2, then we want to find this total probability, but we just add the 2 areas under the curve. So it does satisfy the axioms of probability. So let's look at the normal distribution. And I think most people have heard of a normal distribution. They call it the bell curve, the Gaussian distribution. And it's a continuous random variable, and often sometimes called the Gaussian. It's one of the most fundamental probability distributions in statistics, period, mic drop. And there's several important theoretical properties, and we'll look at a few of them here. So if we let X be a normally distributed, so it's a normal random variable, and then its probability density, f of x, is given by this equation here. So notice that x can take on any value in the real number line. And in this density, there's some parameters. There's a mu and there's a sigma, or sigma squared. And those represent things. So in the normal distribution, mu, it's the mean. It's the expected value of our distribution. It's also the median because the distribution is symmetric and it's the 50th percentile in that distribution. Sigma squared is the variance of our distribution. So if you take the square root of the variance, you get the standard deviation. And it really controls the spread. And so if we plot three different normal distributions with different means, so we have a mean of 10, which is this one, and the variance is 1. So that tells us the spread this way of a density. And then we plot it for 10, but it has this says standard deviation. So the height would be here. And notice that the spread of the data is more because of this standard deviation is bigger than this one. Or if we have a mean of 11, so that's right here, and the standard deviation is 1/2, notice that it's narrower than these other two, right? And so the mean and the standard deviation, or the variance, both it's the same. Well, if you know one, you know the other. So it's not the same, but they're one-to-one functions of each other. Then it uniquely determines that normal distribution. And how do you find probability in a normal distribution? Well, it's the area under the curve. So if we're using this curve to find the probability being between 11 and 12, then we would find this area, and then that's the probability of being between 11 and 12. So some properties of the normal distribution: it's symmetric, it's always bell-shaped. Now it could be a thin bell or a fat bell. That depends upon the variance or the standard deviation. And there's some empirical rules. About 68% of all the data falls within one standard deviation, the mean. 95% fall within 2 standard deviation, and 99.7 fall within 3 standard deviation. And if we were to draw a plot of this, so this ends up being a standard normal distribution, that if we go, which means the standard deviation is 1, so if we go 1 standard deviation from the mean, about 68% of the data fall here. Now, what do you think the area under that curve is? 0.68. It has to be, right? Because that's what we're saying. 68% fall within 1 standard deviation. 95% fall within 2 standard deviations, and 99.7 of it fall within 3 standard deviations. The standard normal random variable. So the standard normal random variable, we call it Z. So if we let X be a normal random variable with some mean and some variance, then Z is a normal random variable, but the mean is 0 and the variance is 1. So the mean is that, and this is how we write it. Z is distributed with a standard normal distribution. Now, probabilities in a standard normal distribution are typically found in Z tables at the back of your book. But now with computers, everything's done on the computer, not in the back of the book. But we'll go over some of the techniques that are used. Now, the standard normal cumulative distribution function, remember that's the CDF. It's a standard normal random variable, but then the CDF or Z is a cumulative probability, and we usually write that with a capital phi. So phi of Z is the probability that our standard normal random variable is less than that value, right? So that really means that our random variable is between negative infinity and Z. And if you were to use calculus, it's that this is how you would do it. You'd integrate the density over those values. Now, if we draw a picture of what's going on, so that's the standard normal random variable. And if Z is here, that's that probability. That's phi of Z. The CDF is Z. Now, one thing. Well, yeah, we'll leave it at that. Now let's use table 2. It's actually a page down to find this accumulative CDF function. Now, in the table, the first column. So Oh, I should probably replace that with a Z. This value goes here. The first decimal of this value. Remember these values, so this could be, 1.67. And we want to find this probability. And we do that in the Z table, table 2. It's a page down, we'll go to in a second. The first decimal is in the first column of the table. Then which it would be, say, the sig. So 1.6. That's looked up on the left side of the table. And then that last digit, or the second decimal, is in the first row of table 2. And since the normal distribution is symmetric, we only need half of the tables, half of the Z values. Okay. So if we want to find this probability, the probability that Z is less than 0.72, to do it in R, you just run that and that's the answer. But to use the table, what's the number again? 0.72. Notice it's the CDF of a standard normal. So 0.7 and 0.2. So you go down. That's the cumulative probability. That's a probability of being less than or equal to 0.72. This. To be less than 1.96, you can find in the table that it's 0.970. And so remember, P stands for, it's the CDF of a normal. And when there's no additional parameters, it means the mean is 0. Oh, that's a mu. And the standard deviation is 1. So that's the probability of being less than 1.96, which is 97%. Now the probability of being greater than 1.96. So if we draw the standard normal distribution, and we're at 1.96, we're trying to be greater than that. That's not a CDF, right? So the table doesn't help us directly. But we do know that the total area under the curve is 1. So these two probabilities add to 1. So if we want to find the probability of being greater than or equal to 1.96, that's the same as 1 minus the probability of being less than it. And these are the types of values, CDF values, that we can look up in a table. So we want this, and then we already looked it up, so that's 0.02. But to do it in R, we use the CDF, but we say lower tail false, which means accumulate this way, and that's our answer, 0.02. Yeah. Now, the probability being less than 1.96. So let's look at this one. Well, in R, boom, it's easy, we're done. But to do it in a table, so here's a standard normal. The table only has values over here cumulatively. We want to be less than 1.96. That's here. But these are, if this is 0, these are positive numbers, these are negative. The table doesn't have it. But this probability, minus 1.96, has the same area under the curve from 1.96. And then to calculate this area, which is the same as this area, we take 1 minus this accumulated area, and then we get this. So, yeah, the probability of being less than 1.96 is the same as the probability of being greater than 1.96, which then we can convert it into a CDF type function, and then we can, which is what that is. Now in R, you just stick it straight in. If you were to say P norm 1.96 lower tail equal false, it'll be the same, right? Because that's the lower tail and this is the upper tail. So it'd be the same. To find probabilities that we're between values, then we have to subtract the CDF of at 0.72 minus the CDF of negative 1.96. So that's what this is. And then we calculated those above, and it's 0.739. Okay, so I got to stop here and we'll pick up in the next video.